So the next random variable that we are going to study is the triangular random variable. Now, triangular distribution actually has a typical use in simulation models. So it says a continuous random variable x is set to follow a triangular distribution with parameters a, b, and c. So a is the lower bound parameter, c is the upper bound parameter, and b is the mode of that distribution where the probability density function is maximized. So it is a triangular shape like this. This b value should be between a and c, and it can also be equal to a and c as well. For example, if b is equal to a, then we will have a perpendicular triangle shape here, or if b is equal to c, again we will have an orthogonal triangle here. And the probability density function is partially defined for the first interval a and b, where the line has a positive slope, and in the second part, in the BC interval, it has a negative slope. And the area under the triangle should be equal to 1. Therefore, the peak point has a PDF probability density value equal to 2 over c minus a. And our linear functions are given in this form. I'm not going to read them aloud, but you can study at home. Now, the CDF is going to be in the quadratic form of functions. And actually, we have already studied those in the third module of this class. So I'm not going to focus on the CDF as well. So we have, again, partially defined quadratic functions in cumulative distribution function. Now, what we need to do is we need to calculate the inverse CDF. Now, I'm not going to show how to calculate the inverse CDF. Why? Because if you want to take the inverse of the quadratic functions, which are monotone, of course, you need to solve for the discriminant and you need to identify the root of the quadratic function here. I'm not going to show how this is going to be done, but if you check the formulas here, they look like that we have the discriminant value in the square root here, and we have the classical formula for the root of quadratic functions. Now, this formulation is true in the end. At home, if you practice to compute the inverse CDF of these quadratic functions, it would be a good practice. The inverse CDF will be equal to a plus square root of r times c minus a times b minus a if your random number is between 0 and b minus a over c minus a. Now, please take notice this b minus a over c minus a is the area of the first triangle. So area of the first triangle here is exactly equal to b minus a over c minus a. If your random number is between 0 and this value, then you are going to use this formula. Otherwise, if your random number is greater than b minus a over c minus a and less than 1, in that case you use the second formula, which is the inverse of the second part. Now let us use this technique to generate random variates from triangular distribution. Again, you need to check first if you are going to use the inverse CDF for the triangular distribution. First, you need to check where your random numbers resides within. So if it is in the first interval here, then you use the first formula. Otherwise, you use the second formula. All right. So let's read the question. The truck fleet of a logistics company moves shipments from Istanbul to Ankara, and the transportation times are observed to be 4.4 hours at minimum and 8.5 hours at maximum, and the most likely transportation time is observed to be 6 hours. So the logistics company has a certain data about the past deliveries, and according to the histogram of the data, what they found as a fitting distribution is a triangular distribution. So 4.5 is the minimum transportation time. Therefore, A is equal to 4.5 in this question. 8.5 is the maximum transportation time. So C is 8.5. And the most likely transportation time is observed to be 6 hours. So B, the mode of the distribution, is equal to 6. So these three parameters are respectively called the lower bound, the mode, and the upper bound of the triangular distribution. Now, we assume a triangular distribution for shipment transportation times. We are going to use the following random numbers again, 0.1175 and 0.6046, to generate the transportation time for the next two trucks. what we need to do is, first we need to check which random numbers are less than b minus a over c minus a, and the first random number is less than this critical value, which means we need to use the first formula to convert the first random number to a random variable. Now the second random number is greater than this value. Therefore, we need to use the second formula to generate the second random variable. So what we are going to do is this: we are going to use the first part of the inverse CDF to convert R1, and here it is going to be 5.34. Now please notice that 5.34 is between A and B, okay? And R2 is going to be converted into a random variable by the second part of the inverse CDF, and here C is 8.5 and the other values are plugged in, and you get a 6.51, and 6.51 is somewhere between B and C, okay? So you see, after checking this condition, whether your random number is less or greater than this value, you are going to generate a random variable which is either less than or greater than B here, the mode of the distribution. So with the second function, you never generate a random variable between A and B, and with the first function, you will never generate a random variable between B and C.